Welcome to the Foundry by Forge College. I'm absolutely thrilled to have you here. Today, we're diving into a brand new explainer on event handling and logs. Now, if you've been following along with our Programming with Anchor course, specifically within the Anchor Framework Essentials module of our Solana Development Tools track, you know we're getting into the really good stuff. We're going to build an observation telegraph for your Solana smart contracts. So let's jump right in and see how we can make our code truly observable. Think back to our previous lesson on instruction and account patterns in Anchor. You essentially built the heavy machinery, right? You crafted the precise gears needed to update the state of your application. But here's the problem. Right now, that machine operates inside a completely soundproof, opaque box. Your program successfully updated the state, but how do you actually prove it to the outside world without ripping the box open? Well, to fix this, here's our master blueprint. We'll be hitting 6 quick steps today: exploring the soundproof contract, designing the event blueprint, emitting the signal, catching those logs in TypeScript, verifying the payload, and finally, prepping for cross-program calls. Let's get into it. Starting off with Section 1, the soundproof smart contract. Without a transmitter, you're completely in the dark. The old way of doing things was honestly sheer agony. Developers literally had to scan raw, unparsed account bytes manually. Just imagine staring at walls of hexadecimal data just to figure out if a simple counter went up by 5. It's terrible, but the Anchor way, it's wonderfully elegant. Instead of that mess, we emit structured, strongly typed events directly into the transaction logs. So what exactly is this mechanism? Well, an Anchor event is basically an automated receipt printer for your smart contract. Technically speaking, it's a Rust struct marked with the event attribute. It acts as a Borsh-serializable typed signal that communicates on-chain state changes directly to off-chain consumers. You do the work, and the contract prints a perfect, readable receipt. Moving right along to Section 2, designing the event blueprint. We're going to draft the exact specifications for this transmitter right in our Rust code, and it's an incredibly elegant 3-step engineering process. Step 1, you add the event macro to your struct. Step 2, you mutate the state in your handler. This is where the actual action happens. And Step 3, you use the emit macro to broadcast that change to the world. Take a look at how lean our CounterIncremented event structure actually is. We only include the minimal fields that off-chain consumers absolutely need to validate the action. In this case, that's the authority, the amount, and the new total. Keep it lightweight, guys. No fluff allowed on our telegraph line. Which brings us to Section 3, emitting the signal. We've got our perfectly designed blueprint, so now it's time to wire up the transmitter. And here's the magic line of code. We use emit followed by our struct and its data. Let me emphasize a golden rule of thumb right here. Always fire the emit macro after the state change actually occurs in your handler. If you emit it before, you risk broadcasting a state that might fail a split second later. We want the payload to reflect the final, updated reality. Of course, no engineering session is complete without a little mild panic, right? You run the code and nothing. The transaction logs are totally empty. Well, before you lose your mind, run through these quick troubleshooting tips. Did your instruction return an error before it could even hit the emit line? Are there mismatched account keys? Maybe an Anchor version mismatch where your CLI and crates are fighting? Or are you simply missing the Anchor event discriminator in your TypeScript setup? That perfectly tees up Section 4, catching logs in TypeScript. Building the transmitter is really only half the battle. If a tree falls in a forest and no one catches the log, well, you get the idea. We need to build the receiver. In our local test environment, we use the Anchor TypeScript client to ask the validator for the parsed transaction using getParsedTransaction. This pulls down all the raw logs so we can actually inspect them. And this is the deeply satisfying result you want to see. Right there in the console, program log, Anchor event, CounterIncremented, followed by our exact data payload. The discriminator tells Anchor this is a decodable event, and we can clearly see the authority, the amount of 5, and the exact new value of 5. The signal has been successfully received. Next up, Section 5, verifying the payload. In Web3, we don't just blindly trust a telegraph message. We verify it against the true on-chain state. Let's look at how this builds our validation strategy. Each event field must be cross-referenced. The authority field, verify it against your provider wallet's public key. The amount, check it against the instruction parameter. And the new value, Literally read the on-chain counter account state directly to ensure it mathematically matches the log. Trust, but aggressively verify. To summarize, this is what a perfect test run looks like. Step 1, confirm the transaction was an actual success with no runtime errors. Step 2, locate that specific event log discriminator in your console output. And step 3, verify the payload fields match the current account state. Hit all 3 of those, and your code is rock solid. Finally, Section 6, prepping for cross-program calls. Now, you might be wondering, why go through all this meticulous effort just for an isolated counter? Well, because this observability matters far beyond a single program. As we transition from Phase 1, single program validation, into Phase 2, we introduce cross-program invocations, or CPIs. Soon, your program will start commanding other programs, and by Phase 3, you're dealing with complex multi-program network tracing. Mastering events now is the essential bridge to handling that future complexity. Which naturally teases our next lesson, cross-program invocation patterns. When multiple machines start talking to each other, these typed event signals become absolutely critical for tracing the flow of logic and state across the entire network. Without them, you're literally flying blind. So I want to leave you with this provocative thought to ponder. When you have multiple smart contracts interacting, which specific event fields would you need to assert correctness across those program boundaries? Think about how you would trace that chain of custody. To explore more about this, dive deeper into Web3, and continue leveling up your engineering skills, make sure to visit forge.college. Thanks for joining me on this explainer. Keep building, and I'll catch you next time.